So in this video we will be taking a look at some of the mathematical preliminaries of electrodynamics. So electrodynamics is a branch of physics that studies the behavior of electric charges which are in motion. Okay. So if a electric charge is in motion, it is studied by electrodynamics, and the complementary branch which studies those charges that are at rest is called electrostatics. And the very first concept that we would be looking at is the concept of a scalar versus a vector. So if we have a scalar is nothing but it is a quantity. Okay, it is a mathematical quantity that is fully described using a number. That means it has no direction. So if we have a temperature map, then this describes a scalar field, because at each point in that map there is a temperature associated with it. So what is a scalar? What is a field exactly? Field is nothing but if we have a quantity, let's say temperature is different at different points. So in order to quantify that, how much the temperature is at different points, we use a concept of a field. So scalar field maps a scalar to every point in space. Let's look at vector fields now. Vector field is nothing but it is a field of vectors. Vector is nothing but it is a quantity which has both magnitude and direction. Direction as in, if we have a force, and the force will have a particular direction in which it is acting. That direction and magnitude is represented by the length of the vector quantity. Based on these two things only, we are defining a vector. So for example of a vector field is that of a weather map or a wind map. Actually, wind map is a example of vector field. So that is what we mean by a vector field, nothing but a wind map. So in this map we are looking at the wind speed at different locations on the map, right, on different locations in the world. That is the wind map. And then we can also look at the concept of gradient of a scalar field. Gradient is nothing but if we have a scalar field and we are having a particular operator which is known as the del operator. It is nothing but I dou by dou x plus j dou by dou y and k dou by dou z. Where this dou by dou x represents the partial derivative of some quantity with respect to x. In this case, we are taking the gradient of f. Therefore, it represents a partial derivative of f with respect to x. And is I, j, k are nothing but the unit vectors in the corresponding Cartesian directions. So for I we are using it for x direction, j is for y direction, and k is for the z direction. This is a three-dimensional formula because it represents the directions in three-dimensional space or three-dimensional Cartesian space. And what is the physical significance of this gradient? Physical significance of gradient is nothing but if we have a temperature field and we are selecting a point in a temperature field. So if we move in different directions, let's say we are having a unit sphere, some kind of sphere of dr displacement, the dr radius centered around the point that we are selecting. Now if we move in a particular direction, the temperature will change, and in different directions the change will be different. And there will be a particular direction in which that change will be at its maximum value. If we take that maximum value of change along with the direction, then we call it a gradient vector at that point. And by mapping the gradient vectors at different points on the scalar field, we can convert a scalar field basically into a vector field. And that vector field is called a gradient field of the scalar field. So like we say, like it is given below, gradient is a space derivative because it represents the maximum rate of change of the scalar quantity with respect to space. And then we are having the divergence of a vector field. Divergence is nothing but it is a dot product of del operator with a vector. Okay. So if we have a point, and at that point we are finding the dot product of del with a vector, then we call it a divergence. Okay. So dot product is calculated in the following way by partially they're taking partially derivative of each one of the components. Okay. Then let's look into the physical significance of this divergence. So the divergence measures if we have a fluid as the fluid velocity as the vector field, then how much the fluid is coming out of a point or going in a point, that is divergence. So if the fluid is coming out, it is called positive divergence. If it is going in, it is called negative divergence. Okay, and here we are representing it in two dimensions. That's why Vx and Vy are only are present. If we are representing in a three dimension, the Vx, Vy, Vz will be present. And if fluid is moving without going in or coming out, then it is called zero divergence. Okay, now let's look into the concept of curl. Curl is nothing but it is a cross product of the del operator and vector field, vector at a point. So it represents the rate of rotation. That means if we have a fluid, how much the fluid is rotating around a particular point, that is represented by this curl. So this is the physical significance of curl. It is nothing but if it is rotating in anti-clockwise direction, then it is a positive curl, and if it is rotating in clockwise direction, it is called negative curl. Okay, and now that we have seen the physical significance of curl as well, let's go into a Laplacian operator. Laplacian operator is nothing but del square, the quantity, the operator del, which is squared, and it can be applied to either scalar or vector quantities. And there are also two equations which use this kind of a operator. They are Laplace's equation and Poisson's equations. And now finally I am going to thank you all for watching, and if you want more videos, you can subscribe to the channel.